Kia ora koutou e hoa ma. Nā mihi nui o te ahe po. It's lovely to see so many names. I don't actually see any faces, but it's completely up to you whether you want to show yourself or not. Thanks anyways for zooming in tonight. It'll be an awesome seminar. We have Jonathan Holmes from BIA Architecture will start us off with an introduction to the passive house classes, introduces also the honest net zero energy building concept known as passive house premium, and has as an example he uses his own house. He's followed by Dean Dunning from Think Solar, who partners with local solar companies around the South Island to provide feet on the ground quality solar services. And Dean will give an overview of solar components, explain how solar works, and how to size solar for happy customers. All right, without further ado, Jonathan, please share your screen and continue with your presentation.
Did that all work? Is that working?
Yep.
Cool. Okay. So yeah, as Car's set out, I'll be going a brief introduction to the different classes that were introduced with solar, and some personal experience with solar on my own house. Plus, I quite like to thank Cara. Whenever we end up doing these talks, I end up doing loads of research and finding out a load of new things that I didn't know before I started. So I'll be showing some things that I learned on this journey to prepare the slide pack. So just to introduce myself, I work for Elrond, passive house consultant, and the range of work that we're doing is sort of energy and carbon modeling now and benchmarking, and more clients are asking to look at the whole sustainability of their entire build. And some interesting things happened during preparing these slides, that I started working with an electrical engineer to look at the entire energy market in New Zealand, and I may mention some things that came up there. So without further ado, so passive house classes, a few years ago, we're very familiar with the focus on energy efficiency and the passive house classic. But they introduced two new classes, Plus and Premium, and we probably focus on the 15 kilowatt hours per square meter per year for heating demand. And this is probably what passive house is quite famous for. But there was an increased focus on the total energy used for the building, and a requirement around a generation, but it's based on the kind of projected footprint of the building, not TFA. If you like, it's sort of like the shadow that the building casts onto the ground. However, probably I'll be introducing this concept of net zero energy building. So we'll start with looking at a single building, and then what happens if we take a Kiwi house on a journey to become passive house. So you'll see on the right hand side, there's how much energy the building can use in total. And then on the left hand side with the picture of the sun is the generation that's required for Plus and Premium. It can be on the roof, it commonly is, and it's modeled in PHPP. There's a PV worksheet for modeling the energy generation. However, I'll be showing my experience, which is not mounted on the roof, it's mounted on the ground, and actually generates a lot more energy than is modeled in PHPP. What I would say, I'm just posing a couple of questions for you, that maybe we should focus more, not just focus on heating demand, but overall energy demand, because every kilowatt costs, and also in the future, we need to use all the renewable energy we can to electrify transport and industry. And the other thing is, given the cost of solar has come down so much, does the ability to put a power station on your roof change what you put inside your house? So these are just questions that I'm going to pose that we'll come back to. So on the left-hand side, we've got a kind of picture of a New Zealand house and surrounded by the electricity grid. And that's very deliberate because we'll be looking at both the house and the grid implications of the passive house classes. And we've got passive house C, which is classic, Plus, and Premium. So if you said the current state is a house that uses 10,000 kilowatt hours a year, Down the bottom, this is split out 7,100 kilowatts of electricity and 2,900 kilowatts of presumably gas or some non-electrical energy source. The average size of a Kiwi house that I'm using for this example is 155 square meters. And this was from, I think, Stats New Zealand, and it's a 2021 figure. And because of the way the calculation's done, this projected footprint, I'm using an assumed footprint of 163 square meters. So if I summarize the current state of a house, it's somewhat uncomfortable and somewhat unhealthy. People tend to live in part of the house, and they close the doors so they don't heat all the house. So, and certainly in our region, in Queenstown, people tend to heat their house to the extent they can afford to heat the house. They're not heating to the full extent to be actually warm and comfortable. So if you go to Passive House Classic, there's no requirement for generation because it's an energy efficient house. They tend to be entirely run on electricity. And if you use the PER demand 60 kilowatt hours per square meter, but that house will now use 9,300 kilowatts. Now, if you compare that to the total energy use of the Kiwi house, it's a small reduction in overall energy use. However, if you reflect on the fact that part of that was electricity and part of that was gas, essentially what we do when we get a very comfortable house, a very healthy house, we can live in any square inch of the house. And in essence, we're displacing the gas use, and we're getting to a very similar situation of overall energy use in a house. And I think this has implications for how we describe passive house, because if we describe a fridge as being energy efficient, it uses less energy, and we assume that the total energy used by the house is less. And I think it's almost like we have an energy dividend by using passive house, and we spend it on getting a whole house that's livable and a whole house that's comfortable and healthy. But overall, as far as the grid's concerned, we are broadly drawing the same amount of energy from the grid. And then what happens is we'll all go out and buy an electric car and plug it into our house. And the grid modeling is assuming around 2,800 kilowatt hours per annum. And that's largely plugged into 80% of people's energy for their EVs is taken from their home, and they drive it during the week. So essentially we've got a passive house now that essentially has a car load, plug load added into it. And we've got a situation where we're now drawing more energy from the grid. So what does Passive House Plus do? So you'll see this demand figure, 45 kilowatt hours per square meter, same size of house, the total energy used by the house, 6,900. That's a reduction overall. So we're beginning to reduce the amount of energy we pull from the grid. We could potentially put in a car. And then we've now added solar panels basically onto the roof, and we're now generating power, and we can now use that to power our house. And if you like, it's a genuine, or as Jason Quinn describes, honest net zero energy. So it's not like we're basically putting a massive amount in the summer and then drawing a massive amount in the winter. That was essentially, we avoid putting that extra strain on the grid. So if you kind of think of 50,000 new houses being built in New Zealand, and 60% of New Zealand's population is above Taupo, we're essentially going to put these 50,000 houses in the north of the North Island and basically plug them into the grid. Now, if we do not consider what that's now doing to drawing demand from the grid, that we're just going to add more demand, and then we're going to put cars on into the houses and draw more grid. So the current government thinking is that we need twice as many power stations. Now, we can demonstrate that not only reducing the energy we need for a house, but if we add solar panels, we essentially get a situation where we can electrify a vehicle and not put that burden onto the grid. If you get to a passive house premium situation, the amount of energy that the house can use is now 30 kilowatt hours per square meter. The reduction is increased, and the amount of solar generation that needs to be associated with the house, either directly or a community scheme, or doesn't necessarily need to be on site, but in New Zealand, pretty much the only way to do that is to put solar panels on the section or on the building. And essentially by doing that, not only Dean will go into these details on the economics a bit, but Transpower has basically said that a solar plus a battery is cheaper per kilowatt hour than pulling power from the grid. So by going down this track of renewables, the energy you're using is more cost effective, and you can run a vehicle and you're not putting that burden on the grid. We avoid all these new power stations and infrastructure. So I looked across at this is a collection of all the passive house projects in New Zealand. They're not low energy built. These are from Jason's site. And I'm going to use the Swan House in particular because if I look across the PER demand for all these projects, essentially without really focusing, some of them are Passive House Plus, but 50% of all these projects qualify for Passive House Plus. So essentially their overall demands come down. They can add solar and become certified as sort of Passive House Plus or net zero energy building. Only 25% of those projects that could be plus have solar installed and are actually certified. So essentially, we are almost doing it without being conscious to get to a situation where we've pulled down demand. I will cover some ideas on how that's possible. I was a bit gutted, to be honest. I think we have the designers and owners of the Swan House here tonight, but actually, whilst that house is Passive House Plus certified, if their solar system was bigger, they would have been the first Passive House Premium project in New Zealand. And I'll go through the details of this because it's very, very achievable for many of these projects to go down this route. So I said that I'd look at the details on this project. This is off Jason's site, so it's a 140 mil timber framing, fully insulated with a service cavity that's insulated in the walls. It's a suspended timber floor. This is, if you had to say this was the way we were building in New Zealand, this would typically be it, although we use concrete floors a lot more. The timber windows, they're double glazed. So when in this warmer climate, further north on North Island, the lengths you need to go to achieve this lower demand aren't excessive. And if you look at where the little picture, the graph to the right, by focusing on that energy demand, that they get to a situation where they can put a smaller solar system or generate less energy and achieve Passive House Plus. If you have less of a focus, obviously becomes more difficult. Hence, I've just tried to show the arrows going between the two X's. So yeah, it's a really good example of the fact that this is really achievable to do for literally 60% of New Zealand's population. Okay, getting to Passive House Plus. Now the graph on this slide is where the energy is split for my own house. So you can see that most of the energy is still heating. Then we have generating hot water. So it's the classic things with Passive House. So to get that overall energy demand down, it's still a focus on reducing the heating demand and then turning your attention to your how you create the hot water. So getting the energy used for the heating and cooling, classic solutions are things like air source heat pumps. And then in my own house, I've got a shower wastewater heat recovery system, which is just a pipe with the cold water supply, goes around the outside, picking up the heat from the wastewater and comes out preconditioned at a higher temperature at the shower and uses less hot water that way. Another classic way is to have a shower head that fires out less hot water. And then looking at your other plug loads. So don't neglect the fact that when you go down to the electrical store and you have a nice label on the front, it may actually cost the same amount of money to go for a much more efficient fridge, freezer, oven, etc. So these are all quite straightforward ways of getting to that 45 or 30. So looking at my own house, so the photograph are, the two red boxes are inverters, and Dean will explain what they are. They've got a Tesla box, which is a Powerwall 2. And the switchboard is immediately above that. The gray box is called a gateway switch, which will remove our house from the grid. And there's a wall box for plugging the car in. Now, immediately underneath that photograph, I've put what PHPP is expecting us to generate. That's the higher graph, and what we're likely to pull in terms of energy, which is below. And I've kind of tried to allocate that total energy demand across each month. Now, top right is what PHPP says, around about 13,000 kilowatt hours generation. And you'll see these screenshots from the Tesla Powerwall is in 2020, it generated 16,824 now. And the energy used by the house is higher because I plugged my car in. And I will explain on the next slide why we generate roughly 22% more energy than forecast in PHPP. And then last thing to mention probably is the Ecotricity logo, because they're just bringing out a new pricing plan for great solar installers like Wanaka Solar, and the import and export rates. So for me, I would normally pay 34 cents a kilowatt hour to import power from the grid. It's going to be chopped down to 18. And then power that I export to the grid, which is quite a lot, that's going to get a boost from 12 cents a kilowatt up to 18.4 cents a kilowatt hour. And simultaneously, my fixed line rentals are going to go from over $1 a day down to like 60 cents. So do check out, and as Dean mentioned earlier, Octopus Energy, which is a UK retailer, has just entered the New Zealand market, which has got even more amazing deals for if you install solar. So getting back to why I generate more energy than predicted, essentially solar panels are tested at 25 degrees, and when they start generating, they'll get hotter, and there's this temperature coefficient become less efficient as they get hot. Now, when they're ground mounted, they get massive amount of ventilation. Plus, I think potentially we get a lot more solar radiation in Lake Howia Flat, which is where my house is, and roughly half my increased generation is due to my ventilation, keeping the panels cool, and half is due to it's just a great place to have solar. So I just big shout out to Passive House Accelerator. If you have not seen this series of 4 videos, they are absolutely fantastic. They go through all the IPCC research on climate change, why we should be doing passive house, but now why we should be doing passive house with solar. So if you haven't seen these videos, just they are absolutely amazing. So I put the link at the bottom of the slide. They're just fantastic to go off and watch. So in summary, I think we should kind of increase the focus on energy demand, look at not just the building in isolation as a home that's healthy and cost-effective to run, but also anticipate the fact we're going to add an EV in and its role within the grid. If the budget's quite tight, basically putting a hot water heat pump in that's using CO2 refrigerant is approaching the same price as putting a power station on your roof. And in Australia, if you're putting a solar on your roof, they would recommend a direct electric immersion hot water cylinder, because you can divert a lot of the power that you generate, which would go off to the grid. You can use basically your hot water cylinder as a thermal battery. Dean will go in around sizing of solar systems, and potentially if you run out of money on a build, what you can do to kind of pre-wire or prepare for solar. And then lastly, there's a saying in the solar side of things, reduce before you produce. And that fits very nicely with the passive house philosophy. If you make the building more energy efficient, if you don't have the high heating demand, you can have a smaller heating plant. If you reduce the overall energy required, you can reduce the size of the solar system that you need to then go net zero energy. So hopefully that's okay. Just want to thank you for listening. And yeah, if you've got any questions at any point, sing out, and there'll be a chance at the end. And I'll maybe hand over to Dean.
Thanks, Jonathan. That's very informative. Does anybody have any questions for Jonathan before I crack into it?
You may have to unmute and then ask a question if you want to.
G'day, Jonathan. How you doing?
Very good, thank you.
Josh here. Quick question: how do you get that ecotricity? That deal, is that new?
Yeah,
coming soon, sort of thing.
Yeah, it's basically being rolled out to their solar installers. So people like Dean, who they recommend ecotricity, that they make their customers are able to go onto that plan.
I'll put you in touch with the girl Maggie at Ecotricity, Josh. That's doing it. It literally got rolled out like last week. Cool.
But
awesome.
Josh, to be honest, I don't understand, because they're going to reduce the cost of me buying any power, which I buy so little, and I make more money when I sell it, and my daily costs go down. So they're going to lose lose quite a lot with me as a customer.
Yeah, I think they might be doing it because the price of electricity is so high at the moment, the spot price. So it must be worth it to them to pay so much for export.
Right.
I think, but it's pretty much double what it's been historically.
But yeah, just I think when you talk to your solar installer, Josh, and they'll be able to hook you up, hopefully. Cool. Okay, Dean.
Okay. Can you see my screen there, Jonathan?
Yeah, that's all good.
Cool.
See people climbing on a roof with ropes.
Yeah, so there's a typical install around here. There's lots of steep roofs. So the ropes are pretty handy to install it. Cool, crack into it. So who am I? I'm Dean. So like Cara mentioned before, I'm involved in Think Solar and also involved in a few solar branches around the South Island, mainly Wanaka Solar where I live, but a few others as well. So we're just trying to build several branches with people that know what they're doing in terms of solar power. In this presentation, it'd be good to have a discussion, so feel free to pipe up at any time and ask me any questions, or just write a question in the chat and I'll jump on it. So I'll start off with an overview of the main components in a system. So we've got the solar panels. So a quick overview. Solar panels produce DC electricity when sunlight hits them. They're mainly made of silicon wafers, although there is other technologies out there and immersion technologies. We generally get an efficiency from about 18 to 22%, depending on the quality of panel you buy. The max efficiency anybody's ever done in a lab is about 45%. And basically what the efficiency means is if you take a certain area, it's how much of that area of sunlight that gets turned into electricity. So sunlight hits a solar panel, generally 18 to 22% of the area will get turned into electricity. With your panels, the warranties are really good now. So you're looking at anywhere from 10 years to this year, SunPower come out with 40-year warranties. So that's pretty amazing. You know you're going to put solar on your roof and it's going to be working way into the future. Jonathan mentioned before about panels are affected by temperature. So the higher quality panel you buy, will be less affected by temperature. The higher quality manufacturers go to great lengths to try and reduce that temperature coefficient so they don't lose efficiency when they get hot. Then you've got the inverter. So your solar panels are wired into the inverter. What the inverter does, it changes that DC electricity into AC electricity that we use in our homes. So we can use the solar to power our appliances. Similar to panels, it's worth spending the money to get a good quality inverter, as like it's pretty much the heart of the system, and it works very hard and it works long hours converting that DC into AC. Modern inverters, super efficient, like you get such minimal losses when converting from DC to AC. So they're about 95 to 98% efficient. And generally with an inverter, you'll get warranties of 5 to 15 years. For a good inverter, the real working life is probably 15 to 20 years. And then you might have to replace it. And with the inverter, it's generally the component that you get your online monitoring and get feedback from your solar system. And different manufacturers have different levels of monitoring. Next, we've got battery storage. So battery storage generally is used to save any spare power your solar system produces, and then you can use it in peak power times or overnight to continue powering your house. Most batteries now provide backup power. So if you live in an area that experiences grid outages, then that can be quite handy. I won't go into it too much, but batteries can be AC or DC coupled, and that just depends on the system you choose to install. And there's advantages and disadvantages to each, but my view on it is overall, as an end user, once your system's installed, you're probably not going to notice much difference on which direction you go with that. With batteries, important to get quality products that generally have much better support. Warranties range from 5 to 10 years at the moment with batteries. Something that's happening with batteries more recently is you can use them to actually charge from the grid and not from your solar. And that can be good financially for you because you can charge when power is really cheap, and then you discharge your battery into your home during peak times. And with some products, you can program that into the battery and it'll actually make all the decisions for you, so you don't have to do anything. Another component that we use are optimizers. So if you do have any part of your solar array shaded for some of the day, then optimizers can be handy because they're able to manage the shading so it doesn't affect the rest of the panels. It just clips on the back of the panel, and some optimizers can actually offer you panel level monitoring so you can compare all your solar panels and see which ones are getting affected by the shade or some leaves. Now this is really important. I think it's essential to have on your solar system consumption monitoring. And this is something that's got better over recent years. Like classically, people would install a solar system and they wouldn't really be getting good feedback. All they'd be able to do is look on the screen of their solar inverter and see how much energy it's produced that day. But now we can have like real-time live monitoring of what your solar system's producing, what you're consuming, and then what's going to the grid, from the grid, or to your battery, or from your battery. And this data gets graphed as well, so you can look back over the last few days, few weeks, few months, and actually see how you've been using power in your house and make improvements on that. Yeah, and also you can use consumption monitoring to manage your energy use with a few automations. And another advantage of it is to help you size your batteries in future. So if you know how much spare energy you've been producing in the past, then you can know exactly what size battery you're able to charge when it comes around to installing your battery. Now, this isn't really a component, but I think it's probably the most important part of your solar installation, is just making sure that you do work with good experienced installers that are going to give you a good system. Like, a bad installation with good equipment is still a bad system. So yeah, I think that's really important. Okay, so yeah, that's the main components in the system. So now I'll take you through how them components come together to make a functioning solar system. And yeah, again, feel free to stop me and jump in if you're not understanding something or you've got any questions. So like I said before, DC power is produced from your solar panels here, and that's wired down into the inverter, and the inverter changes that DC into AC electricity to be used in your home and powers your appliances directly. So this all happens in real time. So if your appliances are demanding power and your solar is producing power, the power will go straight there to service that load. If your appliances are serviced by the solar, then any excess will go into the battery or go into your EV, go into your hot water cylinder, or if you don't have a use for it, it'll go back to the grid and you'll get credited from your supplier. It also works in reverse. So if your loads in your house are exceeding what your solar is producing, then your solar will still feed these loads, but then any extra power that's needed will come out your battery or come from the grid to service them loads. And probably not too far off from them loads or also being serviced from your car battery if you've got an EV. So with the spare power that you have, you can actually automate some loads to come on. So hot water cylinders are great for it. And like Jonathan mentioned, you can choose a heat pump hot water cylinder, or you can actually choose like a classic immersion heater. So an immersion heater hot water cylinder is actually really easy for us to control. So we can control it from the inverter. So if there's spare power being generated, your consumption monitoring will see that. And these I/O ports will tell the hot water cylinder to turn on and take up that spare power. And that can also be used to power like pools, pool pumps, spas, anything really that you want to switch on. There's also this thing called a diverter. So again, that links into the consumption monitoring, and that actually regulates your hot water cylinder element. So it can take the exact amount of excess you're producing and put that exact amount into your hot water cylinder. So it's a really good way of using all your excess and minimizing drawing from the grid to heat your hot water cylinder. And on that note, that you're now able to do that with car chargers as well. So Jonathan and I both got a Zappi car charger, which again, it looks at your consumption and your spare power, and it actually only charges your car with what you've got spare. So it minimizes that load on the grid, and obviously saves you money because you're not buying electricity from the grid to charge your car. So that's how the solar system works. Now I'll talk you through some design aspects that could come in handy when you're designing a house. Several steps we go through when sizing the system. So we've got angle and aspect, and there's a lot of talk around angle and aspect. What's the best angle for my panels? What's the best aspect for my panels? Well, I actually think this isn't as important as it used to be. Like, solar panels used to be really expensive, so it really mattered that you pointed them in the right direction and got the most out of them. Now that solar panels are relatively cheap, it's less important because you can just add more panels if you're not at the perfect angle. In the slide here, here's an example of installing solar panels in Wanaka, where we live, at 15 degrees and then at 45 degrees, the same size system. So the difference in production over the year is about 500 kilowatt hours. But you could make up for that shortfall on the 15 degrees by just installing a few extra panels, and it would make up that 500 kilowatt hours. So what I'm trying to say here is, like, angle and aspect, it's great if you have a perfect angle, perfect aspect, but if you don't worry, like, there's always options now. For the highest energy production, us sitting in the southern hemisphere is pointing north, and it's generally at about the same latitude as you're placed that the angle of the panel should be to achieve the best results. But like I say, don't worry about that too much, because there's ways to increase your production anyway. So if you haven't got the perfect angle and aspect, here are your options. You can add more panels to make up for the shortfall. You can add tilt frames, so you can tilt your panels up to the perfect angle. Generally, that adds a bit of cost to the install, but you will produce more energy. Or, like Jonathan's done, you can ground mount your solar panels as well. And with ground mounting, it gives you a lot of flexibility around what angle, what aspect you can place your panels.
Dean, are you going to cover off like any maintenance that you might suggest for the panels or the inverters? Is it basically plug in and forget, or is there anything you might need to do once it's up and running?
I suppose that, like, for where we install, it literally is plug in and forget. The times where you need to maintain your solar system is more around the panels building up dirt. So if you live around in an area where there's a lot of trees and leaves that could fall on your panels, or maybe next to like a busy road where a lot of grime could build up on your panels, then you may want to clean them once a year.
Okay.
But generally, we haven't seen panels get very dirty. Generally, the rain washes any dirt off; they self-clean. If your panels are installed on a really flat roof and the rain doesn't run off them easily, then it might be worth getting up there and hosing them down.
So would you put some sort of tilt frame if you've got a flat roof?
If it's below, say, 10 degrees, then it's probably worth thinking about tilt frames to increase winter production and of course to help them self-clean. Yeah.
Cool. Thank you.
So shading's been talked about a lot over the years, and there's a big thing around if one panel gets shaded, then it brings the whole array down. A lot of people mention that, but that's actually not the case anymore. Like, technology's moved on, and shading, much like angle and aspect, is not as important as it used to be. Don't get me wrong, you don't want your panels shaded, because any shading they have, it means they're going to produce less energy, but it doesn't have the effect it used to have on the whole array. Yeah, just don't do what's in the picture there and put some solar in behind a big tree, because you probably won't produce much energy. If you do have shading, the ways that you can manage it is one with good design. So make sure you installer like models your system up and installs your panels in an area where there's not much shade. If you do have intermittent shade throughout the day, there's other things you can do. You can install micro inverters, which each panel has its own inverter, and then the shade is managed, sorry, the production is managed at each individual panel. So if you're, like the diagram suggests, if this panel is shaded, it has literally no effect on any of the other panels at all. But in recent years, like quality inverters have a very clever algorithm built into the controllers inside them. So what used to happen when one panel was shaded, the inverter would get stuck on like a low power point, the black and red lines here. And what that would mean is that the whole array would get stuck at a low power production. But with the newer algorithms in higher end inverters, the inverter's like checking multiple times a second to try and correct that power point. So even if your panel's shaded, it'll get corrected quite fast and it'll still get the maximum power out of the whole array. Or the other option is to, just on the shade affected panels, install optimizers, like I talked about earlier. Quite similar effect to microinverters. They manage each panel individually. So solar can be fixed to almost any roof. The easiest roof you can fix to is corrugated iron. It's really straightforward, really cheap to fix to corrugated iron. Tiles is quite straightforward as well. It can get quite tricky when you're, I was just on one today, but installing solar on like a warm roof where there's not any fixing. So it's important to work with the builders and architects to try and get fixing in during the build process. When you're choosing roofing material, like you are better choosing corrugated iron, as it's going to make your solar system cost less. If you go for say a warm roof, then it's going to cost a lot more because of the fixings. If your roof faces anywhere between, if your roof angles anywhere between like 10 and 60 degrees, say, then the best place to mount your solar system, I would say, is on your roof. And anywhere from east to west aspect as well works well. But like angle and aspect, it's not super important to get that northern, or in the northern hemisphere, southern aspect. Yeah, it's not super important.
So on that photograph, Dean, the cabling that we can see is the cabling you run, obviously connecting the panels to each other for the positive and negative, and then you've got, is that an earth cable that you're?
Yeah, so that the earth cable there. Yeah, so you've got this rail system, which this is on a corrugated iron roof. The rail system's fixed to the purlins beneath, and then all these rails are connected together by an earth cable. And then when the panels go onto the rail system, there's a little spiky stainless steel thing called a weave, and that goes underneath the clamps, and it squishes down and earths the panels at the same time. I can't actually see the chat, so
I'm having a look at it. There's no questions yet, Dean.
Dean, if you are looking for questions, I have a few.
Oh yeah.
Can you tell us about hybrid inverters?
Sure. So hybrid inverters, they are an inverter where you have a solar input and a battery input, and everything battery and solar related happens on the DC side of the inverter, and the output of that inverter is still AC. So what that means is when solar electricity is generated, it will push through the inverter and out to your house to service the loads. And then the remaining generation will go straight into the battery. And because it happens on the DC side, it can be quite efficient to charge the battery that way because there's less conversions. And that's what we call DC coupled. So the battery is on the DC side of things. Another battery technology we call AC coupled, which is what the Tesla Powerwall is. So that actually has its own battery inverter built in. So you just have a grid-tied solar inverter, so not a hybrid inverter. The solar power will all get converted to AC. It will service the loads in your house first, and then the remaining will go through the battery inverter and convert from AC back to DC to charge the batteries. So there is a more, well, there's two conversions instead of one, which means it's a little bit less efficient to charge your batteries. But the advantages of that way is it's a lot more versatile during installation, because your battery can be positioned anywhere pretty much. It doesn't have to be near your switchboard or your solar inverter. And it's much better for retrofitting to existing solar systems. So an AC coupled solution can be fitted to any solar system. You also have an advantage that with an AC coupled battery system, your battery can discharge at its full rate as well as your solar inverter. So for example, if you had a 5 kilowatt solar inverter and a battery, the solar could be pumping power into your house at 5 kilowatts, and your battery could also pump another 5 kilowatts in. So you could service 10 kilowatts of load at once. Whereas if it's DC coupled, because the solar and the battery have to go through the inverter, you're limited to whatever that inverter is rated to. If that makes sense.
Yes, thank you. That makes perfect sense. So if I wanted to be grid connected, so not having large batteries, then a hybrid inverter and a small battery would be what I'm going with.
Yeah, probably for a smaller system. Yeah, the problem is there isn't like a lot of, in my opinion, anyway, a lot of good hybrid inverters out there. Yeah, Fronius make one now, which is, well, I do trust Fronius. It's pretty good stuff, but there isn't a good range of hybrid inverters out there.
Okay.
In my opinion, anyway.
Has it been in the past, Dean, people have gone with, say, hybrid, thinking they may add a battery later? This was kind of going back a while when you might have had a hybrid inverter that used a low voltage battery, and then batteries went high voltage, and there was a sort of obsolescence around the battery that you could get hold of to plug into your older inverter.
Yeah, exactly. You could, good point. Yeah, you could actually corner yourself if you got a hybrid inverter and get a battery there and then. That's great. But if you get a hybrid inverter thinking of getting a battery in the future, then you just got to be a bit careful that the battery technology doesn't change, and then you're left with not being able to add a battery to your system. Whereas if you're not adding a battery immediately, then AC coupling is a safer bet, because you'll always be able to AC couple a battery.
Thanks.
We've got a
Dean,
few.
yeah, I have a question from Joshua here. First of all, thank you for the great install on our system. It appears to be working great, and the data output is very helpful. I have 3 topics for question time. Where are we at with V2H bidirectional EV chargers? Can we export from a battery system to the grid? Is there a great energy management system tool out there, like a hub that can allow us to control where the energy comes from and where it goes, with manual and automated controls or consumption hierarchy? Are these what the I/O ports control?
Cool. Thanks, Josh. I'm glad you're enjoying your system. So I'll start with number one, vehicle to home bidirectional charging. I don't have many updates on that, but basically bidirectional charging is something that should be available soon. So what that means is you can store solar energy in your car battery, and then your house can then use that energy from your car battery to power its appliances. So it's kind of like a replacement for installing a home battery. You just use your car instead. As far as I know, Wallbox were bringing out their Quasar charger this year, which has that capability. What I don't know is whether you'll be able to have backup power from your car. I just don't know if it's got that functionality yet, but that would be ideal. Can you export from a battery to the grid? You can. I'm trying to think how you would do it and why. I suppose you would do it if you had a really high export charge or credit. There is more things happening, not so much in New Zealand, but overseas, where you can actually export your batteries to the grid when the grid needs it. So when the grid has high demand, they'll pay you a good rate for discharging your battery onto the grid, like way above the rates that you would usually get. There's a company called Reposit in Australia that they install a device on your home solar and battery system, and you're able to set your price that you want to buy power and your price that you want to sell power. And if it hits any of them parameters, so say the spot price of electricity drops, it'll trigger that parameter and you'll charge your battery from the grid for probably nothing. It actually got to a point last year in Australia where you were getting paid to take energy from the grid because there was such a surplus. And yeah, the opposite as well. If the grid's constrained, then you'll hit that parameter and you'll discharge your solar or battery to the grid and cash in on that. About the energy management system, Josh, I see it as something that needs to happen, but I don't know of one that incorporates like a centralized control where you can jump on an app and control where your power goes. About as far as it's got with that is kind of the automated loads from the I/O ports, car chargers that can use excess power. No, I would like to see that happen because I've got this vision where there should be one app that everyone's appliances can jump on, and you should be able to queue all your washing machine, dishwasher, fridge, oven on that one app. So as you're generating solar power, each one of them just comes on in turn and uses that excess. And if clouds come over it, it should shut down. But that's just a vision. It doesn't exist yet.
So Dean, just to jump in, I visited my old boss at the weekend, and his son uses a system called Home Assistant. So Josh, you may want to check that out. It can be cloud-based, or you can run an app on your phone, and you can install these little kind of tiny wee boxes that can go behind a switch or a socket, and it provides power monitoring, so you can see what that say a washing machine is using or hot water cylinder. But they can also switch that system on and off. You'd probably have to talk to somebody like Dean to do that, because I don't know how wise it is to be switching off circuits and taking sockets off the walls and wiring things in. There is a kind of partner product that Fronius uses. I looked at it during my build. It's a Lexon or Lexone system, but it's not easy. Like, it's kind of a big system that you kind of wire in and you can automate. It's more home automation than sort of energy management. But the home assistant, you can schedule, you can set triggers for things to happen. So you could say, and you can associate it with sensors that measure temperature, humidity, daylight, and you can have CT clamps measuring home demand and home load and solar generation, and they become events that you can link. But yeah, the guy that put it in was a 15-year-old, and I think maybe you need that kind of expertise, or talk to somebody like Dean to open up your sockets and start wiring in. But yeah, have a search on the internet on Home Assistant.
Cool.
And the little boxes are called Shelly. It's pretty advanced stuff, but looks quite simple to put in.
Yeah.
Judging by the chat, you got to be 15 years old to use the Home Assistant. There's also a Home Manager 2.0, which hopefully also works for people older than 15. But I have not heard about it, but apparently there are options. Rob is asking, what about option of DC to the hot water cylinder, no inverter, using it for hot water cylinder only, optionally include a battery?
So you're actually not allowed in New Zealand and Australia regulations to run DC straight into a element. It has to go through a device to chop up the DC, and that's to stop anyone, if it was a fault, getting like a direct current shot. They need to be able to let go. Whereas if it was DC, there's no break or there's no sine wave, so you wouldn't be able to let go. So you're not allowed to do that. And I don't think it would save much cost, and you'd have the downside of, if your hot water cylinder was hot, then the system would just switch off, whereas you may as well either use that in the rest of your home or export it to the grid and get a credit for it. So it is technically possible, but I don't see the advantage of it.
Thank you. Aaron is wanting to know, can you talk about grid-tied systems that still work when the grid goes down, off-the-shelf options, bespoke design?
Yeah, so generally, if you want your system to stay up and running, the best thing to do is install a battery. There are kind of middle of the road options, but they're not great. It's kind of, so Fronius and Delta make inverters that in an outage, they will be able to power an individual plug without a battery, and they're able to regulate the solar power to match whatever load you put on. It's quite limited in what it can do, because it can only power like one 10 amp outlet. So it won't switch over to your home automatically. It's still quite a manual thing. But it is an option. It is an option. It's just not a great one, I don't think.
Thank you. There's a follow-up question asking what percentage of people are installing a battery as well as solar panels? Would you know a percentage?
It's definitely more than it used to be now. I'd say about half of our installs install a battery, and most of the installs they do plan to install a battery in the future once they've seen how the system runs and how much excess energy they've got to charge it.
Thank you. I have another question. What's with the tilt frames in high winds? Do they work with high wind areas, high wind zones? well, particularly considering that we'll probably, in light of climate change, get more strong winds in future.
Yeah, they do. So depending on the wind zone, you just put more in and make sure they're closer together. So as a design guide, with all the racking gear, that you pick which wind region you're in, and then you can figure out how many fixings you need for that area. Generally, we just install to the highest wind zone for every install, and that covers all bases.
Cool. Do you know what became of? There was a while ago. They were available. I'm not sure if they're still available. Transparent panels, well, glass
Yeah.
panels with solar, with PV panels in enclosed. Are they still around?
Yeah, they're still around. So they're called bifacial panels. So instead of having a like a white back sheet, they'll just have glass on the back as well. And what that means is they can absorb light from the front, and they can absorb any reflected light from the ground on the back. So they are still being produced, but they're generally being produced for solar farms, because they can get another, say, 25% output. And they're generally used in areas that are the ground's reflective. Like, so especially good in snowy places. They also come in useful because they don't have any aluminium on the frame. It's just glass and glass. So they can come in useful if you're installing like right on the beach next to the sea, because you're not going to get any corrosion on the glass.
Cool. Anyone else having other questions about general system before Dean continues to sizing of systems? Okay, Sarah asked, do you think installing solar without a battery still limits demand on the grid as a whole, given that you're likely to be drawing from the grid at times of peak demand?
Yeah, good question. Yeah, I still think it does, because if you're not using the solar, it will go back out into your network locally. So businesses, industry in the area will be sucking up that solar power and using it there. So it will reduce demand on like the major lines on the grid. It reduces what needs to come from the dams, the hydros, or the gas peaker plants, or whatever other power plants, because it will be used up locally.
Yeah, I'd probably say if you just install solar, you can probably consume about 50% as a rough guide of what you generate. And then if you install a battery, in addition to that, your self-consumption can quite easily hit 80% plus. Before we started this evening, Dean and I had a chat, and we live in an area that's essentially gets its power from the grid in Cromwell, and it comes up to our region. They're building a lot of houses where we live, and the same thing for Queenstown. And Aurora, who are the lines company who operate, run, maintain that local grid, is basically saying they're already forecasting a bit of a car crash in terms of having issues with the grid already. So lines companies are incredibly keen. They might not say it, but they're incredibly keen for people to take the load to install generation in such places, because they can postpone that investment in upgrading the circuits. For example, I think from Cromwell up to Wanaka, we're talking $30 million to upgrade those circuits, and that'll go straight on our power bills. And Dean was saying that the situation into Queenstown is possibly more dire, and we're already seeing the lines company change the voltages as well, which has possibly bad side effects. But Dean, maybe comment on that wider impact on the grid that you're seeing, maybe for our area, but that might be representative of what's happening elsewhere in New Zealand.
Yeah, I suppose that the demand in New Zealand anyway for power is going up. More things are becoming electrified. There's also electric vehicles, so that puts demand on the whole grid infrastructure. So it's good if we can produce power in a distributed way locally, so we can reduce the amount of power that needs to come from the centralized systems. Okay, I'll just got another question.
Yeah, so that's the question that's asking the opposite thing. So does it actually still make sense to connect to the grid when you get your power from solar panels and have battery storage?
I think it does. If you're close to a grid connection, I think it definitely does. If you're completely off grid and say it's summer, you fully charge your batteries, then your solar panels will just essentially wind down or turn off. Whereas you could be exporting that power, which one, generates you money, and two, it helps power other houses, other businesses in the area. So I think it is overall an advantage to stay on the grid.
Yeah, and you can use the grid as a source of energy in last resort. So, you know, potentially if you have quite a few days of bad weather and maybe the amount of power generation you get from your panels, you may want a little bit of top up from the grid, or you might go down to you log on to Tesla online and buy an electric car, and all of a sudden kind of your energy demand will change, and you may just be thankful for maybe a bit of top up power during the night to power up your car.
Yeah. All right, I'll jump on this next section. So how to size solar for happy customers. Might pull Jonathan in if there's any passive house related energy questions on this one. So I think it's important not to get bogged down in the numbers too much and actually try and find out what your customer wants to achieve, which I think it could be quite easy to do in using PHPP for passive houses, is just be looking at the numbers, but it's important, yeah, not to miss out on like whether your customer wants to obviously install solar to meet the passive house requirements, passive house plus or premium, but whether they're doing it for environmental reasons, they want to be more self-sufficient, they want to get their return on investment, or the passive house level. So I think it's important just to keep that in mind when sizing a system. So one of the first things we would do is we would look at energy use, which again, using PHPP, it's quite easy to give you that idea of the basic energy use. But we've just got to be careful that we, with the PHPP, and correct me if I'm wrong, Jonathan Cara, but we won't take into account the other energy usage such as EVs or anything externally to the house. So it's important that we actually pull them in as well when we're calculating the energy.
So if you've got a sleep out or a rural section that's got a water pump, or you've decided that you've got your passive house and you want to have a spa pool on the deck, or just anything outside your building, potentially, you're looking at the passive house, but there's loads potentially elsewhere on the site.
Yeah, and that's where it's important, and I keep reiterating it, but to keep your customer's vision in mind, because you could look at what PHPP says and be like, okay, we need a solar system for that amount of energy use, but then your customer's spec could be like, I want to cover all of my energy use by solar and batteries, and therefore we'd need to take into account the EV, spa, and all them external energy uses as well. So once you've worked out the energy use, then you need to size your solar system. Like I would suggest just getting like someone who's familiar with solar and experienced in it to actually help you with this. But in our location here, like a unique rule of thumb is if we want to, for every kilowatt of solar we put in winter, it's going to generate about 2.5 to 3 kilowatt hours a day. And in summer, it's going to generate about 7 kilowatt hours a day. Well, that'll be specific to your location, your latitude, the weather conditions in your area. So what you can do, and I think Cara might send this set of slides out, but you can jump on a website called PV Watts, which allows you to put in a system size for solar. So here we've got 5 kilowatts using premium panels. We're tilting it to 20 degrees and we're facing it north. And you get to put in your location as well, and it will spit out some really accurate energy production data. And yeah, so then you can go back and increase your system size until you're happy with the amount of energy it's going to produce at certain times a year, that in line with what you've calculated your energy use to be. So here's where you could play around with should I put them on flat on my roof at 10 degrees, or do I want extra winter production and I'll use tilt frames? Or should I just add some extra panels, increase the system size here to achieve the same output? So you can go back into and have a play around with that. I just got a question here. Is there any benefit of having a few separate panels and batteries separated from a home solar system primarily just for EV charging or a spa pool? I think it's better if it's all integrated as one, especially if you're on a single phase, because all the energy is going to get pumped into the same home network and used by whichever appliances requiring energy. So yeah, I think it's better if it's all integrated. With Passive House, I'm sure a lot of people will be familiar with SketchUp, but when designing a solar system, it's quite good to model it. And if you're already using SketchUp to model the thermal efficiency of your house, you can actually get a plugin called Scallion here. And Scallion allows us to pick an aspect and populate it with solar panels. And that also links into the PV Watts database here. So you can see exactly what your panels are going to produce given the angle aspect, and it will also take into account any shading factors. So say this roof here was shading the array for half a year, then that would be calculated in the energy production calcs. And it's also great when modeling for checking shading, because you can just run through the year, run through each day and see whether it's actually going to get shaded and adjust where you put your panels. Yeah, am I right in saying, Jonathan, that people will be using SketchUp when designing?
Yeah, pretty much. The certifiers tend to say you have to use it now. It was probably a little bit more optional, but it probably isn't now. You kind of have to use it to get all that shading data accurately, and also they tend to use it to pull in dimensional data, make sure you've used the right figures in your PHPP analysis. So I mean, I know you model it, and you might have a row of trees next to it or another building, and you model that for shading. We tend to do that as well. So it would be quite simple to send you the SketchUp model, and then you could drill into detail. So how do you find that Scallion plugin very accurate? Is that really?
Yeah,
yeah,
it's really good because you can add a new panel to the database, so it's got the accurate size of the panel in.
Right.
And you put the wattage in, and it produces really accurate energy estimations.
Yeah, it's a question that's just come in. It's a quite a good question around the sizing and the oversizing of the inverter. And so obviously there's, you'll have a capacity for the inverter and a number of panels with a different size, and the relationship between the two, I guess. Dean, if you could comment on that.
Yeah, hard to get a right answer to this one. Like, you can do both, really. If you do plan to install more panels, like pretty soon after you've installed your initial system, then yeah, maybe oversize the inverter and just use 1 out of 2 of the inputs for your first set of panels, and then that's easy to add to. If you're not sure, then I would just install the right size inverter, and then down the track, if you do add more panels, you literally just add another inverter, and most of them link together and just act like a single inverter. So yeah, it's not a major, and you can do it either way.
What about undersizing the inverter?
Oh yeah, so I mean, it's kind of good practice to say you've got a 5 kilowatt inverter, put 6 or 7 kilowatts of panels on it. You, in summer, when you're producing a lot of power, you will get something called clipping. So if you were to look at it on a graph, it would go up and there'd be a flat top across the line on the graph, and that would just be clipping off midday production because the inverter would reach its limit. There's been studies done that that's an efficient thing to do over the whole year, because what you gain morning and evening from having a bigger array than your inverter is more than what you lose in that couple of months in summer where you might be producing more than your inverter can output. So it's a good thing to save a bit of money on having like the next size inverter up, but the experiences our customers have had is it annoys them seeing that bit of power getting clipped off the top. So it might be like a practical thing to do, but people do get annoyed that they're just like, oh, I could be producing that extra little bit. So yeah, when designing as well, like, don't go too small. And I say that, I probably haven't said this in the past, but you just see everything's getting electrified. People are getting electric vehicles. There's always extra electrical loads, and export rates to the grid is going up. So make sure you put a bit in your solar system as well. You don't have to design it so tightly. Like I can put here, we've never had a customer come back to us and say, oh, my system's too big. Everyone's pretty happy with producing lots of energy. Whereas we've had customers come back that have installed smaller systems and they want to add extra panels. So yeah, just keep in mind, there's always then future loads, and I don't think you can go wrong. Obviously, if budget's a constraint, that's fine, but yeah, just don't go too small. Got a question. If I was to install an AC coupled inverter, which elevation, east, west, north, percentage of panels would you recommend to go where? Okay, so if you were installing panels on a north aspect, then I'd say, for example, you install a 5 kilowatt inverter, then you might install anything from like 5.5 to 7 kilowatts of panels. If you were doing it on an east-west aspect, and generally if your roof is east-west, you'll install panels on both sides. You could oversize them even more. Like you could put 7+ kilowatts on, because you're unlikely to max out the inverter because the sun's coming up in the east. It'll be on the eastern panels, and as it moves around, it'll reduce the east output and increase the west. So you're not going to overload your inverter that way. but I suppose it is case dependent as well. We would just model that and keep modeling. If we put a certain amount on the east-west, how much is it going to produce, and is it going to meet the energy demand?
There's a previous question, Dean, from Josh saying, can you have two inverters on one array, or do they each have their own designated array? I suppose this might also come into the wiring in terms of using the inputs on the inverter as well. So maybe you can talk to.
Each array has to have its own inverter. So each inverter has two inputs, which can take two arrays essentially. But you could have like one big roof with like 5 different arrays on with 5 different inverters, but it would just look like one solar array. But it does have to be split down in what we call strings. So generally strings of up to about 12 panels will wire back to each input on the inverter. So if you had, say, 36 panels, you'd probably end up with 2 inverters. The max we can do on one inverter is about 22 to 24 panels, and then you end up getting 2 inverters. But that also depends on wherever you are in the world, like the rules around installing solar. Some places you can have much longer strings, but in New Zealand, we have to stay under 600 volts.
Speaking of rules, Dean, is there any situation you can think of where you would need a building consent to install a solar system?
No, I've never come across needing a building consent. For solar hot water, you need a building consent because there's much more weight on your roof. But for solar PV, the only consents that are needed occasionally is resource consents around like the look and visual impact of the array. Did you have to get a resource consent, Jonathan?
No, because it varies by council. You used to have to get one, and then Queenstown Lakes District Council just then switched to wanting you to fill in a form to let them know you were putting solar on the roof. But you're right, there are rules around different colors on a building, and they like the council has rules around matching a dark roof with dark panels, if you like. I did get a really strange question asked on my building consent, which was what color are the panels? And I think it was probably obviously the panels, the main part of the panel is black. It might have been a question that should have been what color is the frame of the panel, because typically they're silver, or you can get them black. And I think our council likes you to kind of go with dark panel and dark frames. But yeah, I thought it was a really strange question because I've got this massive racking system which is shiny silver, so I kind of thought it was a little odd. But yeah, they used to have rules. You also used to have to fill in a form to send to the network company to get permission to connect to their grid, and there's been changes to that in terms of it used to be quite expensive, and then they used to just do it for free. So it can.
It's gone expensive again now.
Yeah.
It was free for a while, and it's yeah.
So I generally say you have to check with your local council, and where I'm staying at the moment is Nelson, and they actually give you a grant towards installing solar. So it might not just be paperwork and approvals; they might give you some money too.
Really? Interesting. Yeah. One last design consideration is whether to choose to add a battery. Yeah, and that comes back to your customer's vision again, I suppose. Like if self-sufficiency is a priority of theirs, then a battery's probably quite important to them, so they can save their spare power and use less from the grid. If backup power is desired, you pretty much need to have a battery for backup power. There are the options I talked about earlier, but they're not full backup power. They could keep like a fridge going or something that you'd plug into an individual point. So I'd say you'd need a battery. Some people install batteries because they want to be that early adopter and support the technology. That's probably one of the main reasons I've got one, but I do really enjoy having a battery. And if return on investment is not the main driver, then if it is a main driver, then a battery might not be for your customer, because it's hard to work out the calculations, but the capital cost of batteries tend to not be great for your solar return. Like normally your return would be better without a battery, unless you're using your battery in a particular way where you're being quite smart with it.
Are there any rules about where you can put the battery, Dean? Because in Europe, you could probably put your battery in your living room, but that's not the case in Australia or New Zealand. So are there some design, when you're looking at a floor plan and thinking my switchboard's going here and my inverter's going there, and where I put my battery?
There's actually there's a standard that's come into play in Australia last year. It's 5139, and there's a lot of constraints around where you can put a battery. In New Zealand, we share the same standards, but in New Zealand, we're not very up to date. So that standard isn't in play yet, and it's confusing a lot of people. We're in New Zealand, we still work to the 2005 inverter standards, by the way.
Would a battery always have to be lithium, or would an old AGM work as well?
I mean, an AGM will work, but it's not designed to charge and discharge fast like a home battery needs to. Like an AGM generally goes through a charge cycle of like 7 or 8 hours, where you can charge a lithium battery from pretty much 0 to full in like an hour. So lithium's much better suited to home storage. Yeah, and in terms of batteries, about half our customers are adding batteries, and most do plan to add them in the future, or some people want to use their vehicle as a battery in the future as well.
So do you pre-wire, like are there situations where budget's tight, I'm not going to put solar on, but I've got an electrician on site or the scaffolding in place, do you recommend pre-wiring? And does that go as far as pre-wiring for batteries, or is that a bit difficult because you're sort of guessing what the technology might be?
Yeah, I would get in touch with your installer on that, because sometimes it is worth pre-wiring. So if the cable runs are really difficult once the house is finished, then it's definitely worth pre-wiring. And probably for passive house, because of the airtight membrane, it makes sense a lot of the time. So you're not having to try and drill through it after the fact. For batteries, it's a tricky one, because you could pre-wire for a certain type of batteries, and the cable entries are all different on all different batteries. So you could go to the work of pre-wiring for it, and then if you go to install it or carry on with a project a year or two later, the product may have changed, and then your pre-wiring isn't in the right place. So for a battery, I would recommend just talk with your installer and maybe try and leave an area free close to your switchboard, so you don't need to actually do any pre-wiring, but it's easy to get wires from your switchboard to the battery. And then on the battery front, it's also, when going back to sizing your solar array, just make sure you size your solar array so it's going to produce enough energy to charge a battery. You wouldn't want to be in a situation where you've bought this battery, which they cost quite a bit, and then you don't have any power to charge it, so it's kind of pointless.
Cost-wise, Dean, or percentage-wise, where would you think where's most of the cost? Where does most of the cost go for a solar system? Is it the inverter, the battery, the panels? What's the percentage there?
If we're talking just solar without battery, I'd say about roughly 80% of the costs are in the solar panels, inverter, and and then about 20% is the installation. Batteries probably like close to 90 or 95%. The cost is in the product, and then small install cost. Which battery prices, although they've gone up because of the supply issues lately, they should come down in price as more and more battery manufacturers get on board. There's a huge drive worldwide towards batteries at the moment, which is good.
So does the battery sort of double the price of panel and inverter again, or is this?
Yeah, so say you installed an average size solar system, which would be say 5 or 6 kilowatts. If you installed, say, one of these batteries, a Tesla battery, you would expect to double the cost of your system. Saying that, like the larger batteries, there is a bit of an economy of scale, so they tend to be the cheapest cost per kilowatt hour. Whereas if you install a smaller battery, you actually still need all the same infrastructure, and you just have a smaller battery, so that, yeah, the cost efficiency isn't as good.
Are all batteries created equally, Dean? Because the Powerwall has a heat pump in it to warm it up and cool it down.
Yeah, that's a good point. So yeah, I don't know if you can see my cursor, but in these batteries, where the writing is, that's where the batteries come up to in this area. And then there's actually a heat pump to heat and cool the batteries, so it keeps them at a constant temperature, which prolongs the life of the batteries. And then there's also a built-in inverter here as well to transform the DC into AC and vice versa. And no, all batteries aren't created equally. There's varying degrees of control you'll get over your batteries, and probably Tesla is at the forefront of that control. It's got a very good user interface where you can set your reserve on your battery. So with a battery system, you generally leave a bit in your battery in case you have an outage overnight, so you can keep your lights and your fridge and whatnot running. And Tesla is the only system I've seen where you can actually just jump on the app and actually change that reserve, which was actually really handy the other day. You were away, Jonathan, but we had a pretty big storm come through here. So you just jump on the app, put the reserve up to 100%, so your battery stays fully charged. And then if the power goes out, you've got a whole battery to keep you going. Whereas I've seen other products which you can do that, but you have to get your laptop out and log into the inverter and change that.
The Tesla battery has a feature called Storm Watch, which is kind of like a teenager on the internet is always surfing the net, looking at weather forecasts to see if that storm's going to hit. What is that? That's a feature that obviously works overseas, but does that work in New Zealand, where the battery itself self-regulates how much power it might need by looking at?
I don't actually know. I will ask that question. I haven't seen that feature work in New Zealand.
Yeah. Okay.
So I don't know whether it is on the app, but I just don't know whether it would work. I'll find out that.
Cool.
Dean, while we're on favorite brands, could you give us some favorite brands of yours?
Yep, sure. So Tesla's probably like ticks all the boxes for home battery storage in terms of like, it's quite a big battery, so you get plenty of storage. It's got a very good changeover time in an outage. It's pretty much UPS, although they don't rate it as UPS. And it's got quite a high charge and discharge rate of 5 kilowatts, and it can even peak at 7.5. So that kind of ticks all the boxes. But other products I would trust is the Fronius hybrid inverter that works with BYD batteries, which is a huge battery manufacturer in China, and they're also one of the biggest electric vehicle producers. So BYD, definitely a good choice, quite reliable. There is a battery manufacturer in Australia called Power Plus Energy, they've created a battery module which has got a really good feature of it stacks in like a server stack. And each battery module has its own battery management system. So what that means is you can add to your battery bank forever into the future because each battery is managed individually. So if you're thinking of expanding your system, but you don't know when, then batteries can be a good idea. We tend to use them more in off-grid because people that go off-grid, they most likely will want to increase their battery bank at some point. Or over time, say you're 10 years down the track and your battery bank has lost capacity, then you could add another module to make up that capacity.
What about panels, Dean? Have you got any favorites?
Yeah, like with panels, there's so many good panels out there now. Like I said, some are even doing product warranties of up to 40 years. Some of the brands that I would like are like SunPower, Q-Cells, Hyundai, LG, although LG have exited the solar game completely, so they don't make panels anymore. What's another one? And then there's all the Chinese manufacturers, like a lot of them are really good as well, like Longi, Jinko. Yeah, there's lots of brands of panels. I would just be, when you're looking at a panel, I would be looking at its product warranty mainly, which ranges from like 10 years to 40 years. And I would be gauging the manufacturer to see whether they're likely to still be around for the warranty period. Which I think LG took everyone by storm there because they were like one of the highest end panels you could get, and they did exit the solar game, which they're still supporting warranties, but yeah, it's surprising. Everyone thought they'd be around forever.
Thank you.
Dean, you mentioned earlier that, well, a good system badly installed is still a bad system. So if I'm considering putting a solar system in my house, how do I know if the installer is any good? What would you look for?
I would maybe ask. Well, it depends on what in depth you want to get, but you could ask, like, if you could speak to some other customers they've installed solar on, maybe see if they've got any like good reviews online. Like if they've got consistent negative reviews, that's not a good sign. Because you want to have someone that's probably get someone that's local, because if you need any support, it's pretty hard to get support off like out of town companies. Like it could be something as simple as your inverter's dropped off the internet and it needs reconnecting. Someone local can like stop by, get it back online for you in 10 minutes. Whereas you could be waiting for months for an out of town company to come and do that. And it's also good because if you want to expand your system or add a battery, like you've got someone there who's familiar with your system, can come around, check out what expansions you want to do. Yeah, and I suppose recommendations of friends that have had a good experience. That answers your question.
Yes, so there's no sort of certification industry standard or something that I know if someone has this seal of approval, then they know what they're doing?
No, not in New Zealand.
Okay, thank you.
Yeah,
thanks.
There is overseas, like in Australia, but you can be Clean Energy Council accredited. In New Zealand, there is a body called CANs, which is like a self-appointed solar body, but there's no certification that you're a good installer. Kind of just like a membership fee.
Would be good to have a certification scheme, wouldn't it?
Oh, it'd be amazing. Yeah, it'd be really good.
Yeah.
Push the standard of installs up for sure.
Yeah, cool.
Just got a quick question, Dean.
Yeah, go for it, Josh.
So the panels, I guess the panels I've got have got a warranty for 25 years, and that they're going to keep producing electricity to 80% of their capacity after that.
Yeah.
So essentially 100 years from now, they'll still be making maybe 20% or some level of electricity. Is that expected?
Yeah, I'd say so. I don't know. Talk to you about the
100 years is a long way out, but it was more back to the battery. So the battery has got a warranty of 10 years.
Yeah.
And return on investment on batteries is sometimes factored as 10 years.
Yeah.
What happens to a Tesla Powerwall after 10 years? Is it degrade very quickly after that, or is it expected to sort of slowly degrade? So you know, might be at 50% after 15 years or something like that. Do you have any experience with that?
The expectation is like for lithium batteries, they degrade in a linear fashion, or quite linearly. Unlike lead acid batteries that can be going and going and then just drop off and be dead. So the warranties on batteries are generally for 10 years, and that allows for a certain amount of degradation. So for a Tesla Powerwall, they will warranty your battery to still be above 70% after 10 years. And you'd expect to keep on operating that battery for 15, 20 years, but obviously with more degradation. I suppose the biggest data set we have on battery degradation at the moment is in EVs. And from my knowledge, the Leafs have actually performed pretty well, which is probably the Leafs and Teslas have been the longest EVs out there. Tesla batteries have performed exceptionally well over the last 10 years in their cars because they've had liquid cooling in the batteries from day one. Leafs haven't had any liquid cooling, so they do show more degradation than, say, Tesla batteries. But I think people are pretty impressed still overall with how they're lasting. So what's the difference between solar on a regular house versus a passive house? I'd actually say there's not much difference in solar, but there's a lot of difference in how them two houses use energy. But for a solar or passive house, you would still take the same approach when it comes to sizing and installing a solar system. So what is good is solar works much better with passive houses. You've got less of that disparity between summer and winter energy use. You've got a more level energy use throughout the year, so it's quite easy to size a solar system to do all your energy needs year round. Much easier to become self-sufficient if you live in a passive house. So here's some graphs I pulled from my house, which is definitely not passive. And this is Jonathan's solar array living in a passive house. So these are both similar size solar systems. They're around 10 kilowatts. Similar amount of people in the homes, doing the same things, cooking breakfast, whatnot. What these graphs show is the blue is actually the solar production. So you can see our solar production follows a similar trajectory, except here on Jonathan's, he was off grid for a couple of months by accident. And the purple area shows energy consumption from the grid. So you can see in my house, around April, we start heating the house. And although we've got a reasonable sized solar system, it still doesn't produce enough energy to cover our heating demand. And we actually pull a lot of energy from the grid still in winter to keep our house warm. if you look at the passive house version, look at the purple parts of the graph, it's pretty much the same as summer. Like, we've not used hardly any energy from the grid summer or winter. So really self-sufficient, not relying on the grid much. Massive difference. Like I've seen before from your slide, Jonathan, you used 900 and something kilowatt hours over the year. Like, I look at so many power bills each day, and that people use that every month.
Yeah, I have to say, probably we both have a house and an EV, and it's the EV that introduces the unpredictability in the power use, and also that interaction between charging the EV and having a charge in the battery to run your house overnight. And sometimes that I screw it up, and I'll plug the car in and it'll suck all the power out of my Powerwall and put it in my car. and then the next day the sun comes up and is really strong, and I wish I'd just left it in my battery. What I probably would say to Dean's defense in his house, because he has done some retrofit activities, and the first thing he did is put insulation in his ceiling, and basically couldn't believe how cost effective insulation was. Probably thought it was going to cost him about 10 times the amount, and it got delivered, and he thought, well, so you put ceiling insulation in, made a big difference to the house. And I think it must be an old picture of your house, because it's got the green frame, metal windows, and is swapped to UPVC, and that's probably reduced his heating demand by about a third.
Yeah, it made a big difference.
That and removing the wood burner is always a good move, because he had a big hole in his roof letting the heat out when he didn't have the fire lit. So that I think his kind of house has got a lot better. But
yeah, we've done about as much as we can, and I did toy with trying to make it airtight, but I think it's just really hard to retrofit that feature.
But I think it's a good graph. It's kind of like reinforces the reduce before you produce. We've got the same size solar system, and we could have got away with half the size potentially, but it certainly provides the power to plug the EV in.
Yeah. So a little bit of a section on what lies ahead for solar. So solar technology is pretty good at the moment. Like, it's really good actually. But there are some interesting things on the horizon. So I'll just go over what I see changing towards the future. So solar panels, we are seeing like efficiency increases in current technologies. And that's been happening for a long time. Like, the solar panel manufacturers, they're always looking for small ways to slightly increase efficiencies. So every 6 months to a year, the same size panel will produce a few more watts, and I've seen that be the case for the past 7 or 8 years since I've been into solar. There is, like I said before, there is like other technologies out there which do produce a lot more power, like they're 45% efficient, but they're still in the lab at this point, not commercially available. So something else to look forward to in the future is new, cheaper solar materials. So there's actually a lot of materials that can have that solar effect. When light shines on it, it produces electricity. They've even developed like an organic solar that you can grow. Generally, they're like a lot lower efficiency than the current silicon technologies. But if you could grow solar, you could just keep on growing it. I think they're struggling just to stabilize that and stop it dying at the moment. There are technologies like thin film technologies, which you can put on windows to produce energy. So you could have like skyscrapers covered in thin film solar panels as their windows, which come in all different colors. yeah, and there's solar technologies that can be produced a lot cheaper than the current silicon, because the silicon takes quite a lot of energy to melt it down and make ingots, whereas there's some technologies that you can avoid that step. They just need to be commercialized. So probably a few years off still. Larger panels, so not so useful residentially, but commercially, like you can get panels up to 600 watts as we speak, and they're getting bigger and bigger. So what that means is for solar farms, there's just less infrastructure required to mount the solar panels. So it should bring the cost of large scale solar down more and more. And solar panels are also being used in different ways. So down here, we've got a floating solar farm. And that actually serves two purposes. One, to generate energy, and the other is it stops as much evaporation happening. So these get installed on reservoirs. In India, they've done quite a big project where it's not actually floating, but they install solar over their canals, like a big continuous bridge. And again, it serves two purposes. It stops the water from the canals evaporating or reduces it, and also generates power for the local areas. I think this picture here is from Germany, and this is a noise barrier along the side of a highway. So they're using the bifacial panels here. So it's still letting light through onto the road, but it's just taking advantage of producing power right the way down the roadway. We've seen an emergence of what's called building integrated PV, or BIPV. There's a picture here of the Tesla solar roof. So there's Tesla and a few other companies are making like roof tiles that you can just roof your house with instead of mounting solar panels onto your roof. Your solar panels are your roof. And so there's them, and there's also like building facade panels, so you can actually have the facade of your building as solar, so it's producing energy. And there's also agrovoltaics, which is becoming more popular. So you're using solar panels over your crops, so to reduce like evaporation of the water from the soil, also generate energy. And in some harsh climates like where we live in summer, it can like shade your plants somewhat so they don't get roasted, and still let enough light through to grow.
Sorry, Dean, just how available are those other types of solar panels?
Like we can get them to order. Like then you wouldn't. Oh, do you mean, sorry, the building integrated ones?
Oh, either or. You know, if I'm building a shed, you know, can I build the roof out of solar panels and clip them together and seal it up and you make it as a roof? Make it a roof. You know, if I'm putting up a fence, can I make that fence out of solar panels? You know, with the price of fence claddings, sometimes it'll be almost cost effective.
Yeah, you're right. So a fence, that would be no problem. You would just get some bifacial panels.
And they're available in New Zealand, bifacial panels.
Yeah, they are actually. Yeah.
Yeah. Similar pricing, or?
No, it is a bit more expensive just because there's more cost in having 2 layers of glass.
Mm-hmm.
Yeah. But for the roof tile solar, if you live in California, you could use them for your roof, but not in New Zealand yet. Yeah, but in the coming years, that'll become, I'd say within 10 years, that might be quite normal to have your roof made out of solar tiles.
Well, glass seems like it have a longer lifespan than corrugated iron too, so it probably lasts longer.
Yeah. For inverters, like we're just seeing inverters come out to allow more flexible design. So I talk about inverter having 2 inputs. The newer inverters that are coming out have some of them have 3 or 4 inputs, which just allows for more flexible design if you've got multiple roof aspects. There's better consumption monitoring in the newer inverters, and that's getting better in terms of like more information is available. You can look at your energy use in a nicer way and understand it better. There's more and more integration with appliances like hot water control, vehicle chargers, switching appliances on and off. That's an area that's going to be huge, I think. Automation of appliances. And then, like I say, it's not quite there yet, but inverters being able to do backup without batteries, I think that's on the horizon at some point. Batteries, so what I see happening to batteries in the future, price reductions. So as manufacturing increases for batteries, we should see prices come down and energy density increase. So energy density is just you get more battery for the form factor. As more research and more data is coming in from batteries, better reliability in batteries, and I think we'll start to see warranties longer than 10 years for batteries. A big thing will be more integration with the grid. So it's kind of in the early stages, charging from the grid and discharging to the grid, but I see more options growing for being able to integrate your battery into the grid and the bigger picture to be beneficial to yourself and beneficial to the grid. And that doesn't stop at home batteries. That's using your car in that way as well.
Excuse me, Dean. Do you see, like, there was mentioned by Keanu Orr, the state housing provider, that they may use microgrids, that they're beginning to put solar on their social housing projects and may consider a microgrid. Do you see that being used a bit more in New Zealand?
I do, but I mean, and it's easy to set up. Like, the technology's there, it's not that complex. It's just about how you set up accounting for that power between all the houses. Okay. And how you avoid fallings out. Like, Jim down the road's used all our power, we have to pay the bill. Yeah, so it's more in terms of like aggregating the data for people's power use, I think, is the challenge in that area. But if there's a retailer willing to get on board and actually solve, I think it will be easy to solve. You just need the means to do it. Don't know if that answer makes sense, but I do see it becoming more of a thing, but there are some challenges around accounting for power use.
Okay, thank you.
Yeah, and moving forward, I think a big thing is, just mentioned it actually, but integration with the grid. So like, I think ways will emerge, like a better models to trade power. So you might have like peer-to-peer power trading between you and your neighbors, which might work off some kind of blockchain system where there's real-time data being recorded. So if you're exporting power and somebody's using power at that same time, then you can actually trade power that way and just incur the network charges for that power traveling along the network. But your excess and someone's usage could cancel each other out and trade power. There'll be more ways to get on board with exporting power from solar and batteries to service the grid. So like the reposit system I talked about earlier in Australia, you could set your prices. If the price hits the high price you've set, and your battery will export to the grid, which helps you financially and helps the grid service its power demand. And that goes on to the same thing, charging your battery bank when the price is low. You can do that manually at the moment. On some products, you can actually just set up your tariffs, so it will automatically charge when the price is low or free. But I think that will become reactive to what the grid's demanding in the future. And all these things, they help to balance the grid as well. Like it works in everyone's favor. I see more resilience with distributed solar and battery storage. So as there's a higher penetration of solar and batteries in certain regions, like if there's a grid outage somewhere else, then we might be able to keep the grid up and running in certain areas instead of the whole grid going down. And pretty much to wrap it up, when we're talking about solar and batteries being used in this way, we're not too far off, I don't think, from EVs being part of this model. And I think they're a huge piece to the jigsaw. Like generally, if someone's got an EV now, you've got like 40 kilowatt hours to 100 kilowatt hours of batteries, which is far bigger than most home battery systems. So it's massive energy storage potential for a grid to tap into. So integrating EVs into this puzzle has got to be the way forward. Yeah, that's about me, really. That's all I've got to say. So thanks for listening. And if you got any questions, fire away.
Thank you so much, Dean, and also Jonathan.